Welcome to Lesson 7D, Introduction to Moving Normal Shocks. In this lesson, we'll discuss moving normal shocks, and I'll show how their analysis differs from that of stationary shocks. We'll also compare shock equations in absolute and relative frames of reference. Let's consider a moving normal shock. Could be from a blast wave or a shock tube, for example. And let's first look at an absolute reference frame. In this case, the shock is moving to the left, and in this case to the right. In either case, we define 1 as before the shock, and 2 after the shock, with shock speed Vs and gas speed behind the shock Vas. The shock moves into still air or quiescent air, since we're in an absolute reference frame, and speed V2 is the same as Vas in either of these cases. Let's define Ms as the shock Mach number, defined as Vs, the speed of the shock, divided by A1, the speed of sound, in region 1 ahead of the shock. It turns out that this is the same as M1 in our normal fixed shock reference frame, so M1 must be greater than 1 in order for there to be a shock. I also comment here that the air behind the shock, in region 2, follows the shock but at a lower speed, Vas. Let's analyze this case in detail. First, consider the stationary shock frame of reference, which I'll typically abbreviate FOR. For either of these cases, we're in an absolute frame of reference. Well, in the stationary shock frame of reference, we have 1 before the shock and 2 after the shock. And the only difference from most of our discussion so far is that the flow is from right to left instead of left to right. And we have Mach numbers M1 and M2, speeds V1 and V2, T1 and T2, etc. Now recall our equations across a shock in this stationary shock frame of reference. In other words, the shock sitting still and the gas moving here from right to left, as for example in a converging-diverging nozzle where the shock is stationary, with flow sonic at the throat and supersonic before the shock, subsonic after the shock. We've discussed this many times, except in the past we've always had flow from left to right. But the equations are the same as previously. Conservation of mass, ρ1 v1 is ρ2 v2. We'll call this equation 1. The momentum equation, p1 plus ρ1 v1 squared equal p2 plus ρ2 v2 squared, equation 2. And conservation of energy, h1 plus v1 squared over 2 equal h2 plus v2 squared over 2, equation 3. These are the equations that we've used many times already, again valid for a stationary shock frame of reference. It turns out that these 3 equations still hold in an absolute reference frame where the shock is moving, but we have to be very careful here. I caution that in these equations, in the stationary shock frame of reference, V1 and V2 must be defined relative to the shock, and that holds whether we're in a stationary shock frame of reference or a moving shock frame of reference.
I like to work in the relative reference frame. Ah!
I'm not surprised, Albert. I'm not surprised. Let's consider the absolute frame of reference, which I had sketched previously for the case where the shock is moving from left to right. In that case, V1 is 0 and V2 equal Vas. To transform from the stationary shock frame of reference to the absolute or moving shock frame of reference, where V1 is 0, we have to subtract Vs from V1 and V2. I'll show this by also sketching the stationary shock frame of reference. Again, the flow goes from 1 to 2 across the shock, but here the flow comes in from right to left at speed V1, and on the other side of the shock the speed is V2. So to go from here to here, we subtract Vs. Thus, transforming between these 2 reference frames, this V1 equal the absolute value of V1 minus Vs, where we're using this V1 here. And I use absolute value signs because these are speeds, not velocities. They're magnitudes only. Well, this V1 is 0, so this becomes 0 minus Vs, or Vs. which of course is greater than 0 since it's a speed. And this V2 becomes this V2, which is VAS minus VS, absolute value, which is VS minus VAS, since VS is bigger than VAS, as we can see here. Thus, relative to the shock, V1 is the same as VS, but V2 is not the same as VAS, but rather it's VS minus VAS. This is how we transform from this moving shock frame of reference to the stationary shock frame of reference, where these speeds are relative to the shock. In other words, if you're moving with the shock, so you see the shock as stationary. Now we'll plug these equations into our conservation equations across the shock. But first I'll give a quick summary, since this can be very confusing, where I'll compare the absolute frame of reference and the stationary shock frame of reference. Again, for a shock moving from left to right, Vs is the shock speed and Vas is the aftershock speed, since this is a moving shock. And here V1 is 0 and V2 is VAS, and we define the shock Mach number as Vs over A1. In the stationary shock frame of reference, or fixed shock frame of reference, V1 is supersonic from right to left, and V2 is subsonic after the shock, as we're used to. In this case, V1 equal Vs, and V2 equal Vs minus VAS from our transformation above, and here M1 is V1 over A1. Some comments comparing these two, and since V1 equal Vs, M1 and Ms are the same. What about M2? In the absolute frame of reference, we'll call this MAS the Mach number after the shock, and we'll define it as VAS over A2, whereas in the stationary shock frame of reference, we define M2 in the usual way as V2 over A2. Comparing these two, since V2 and VAS are not equal, M2 does not equal MAS. Another comment is that you can calculate M2 to use in our equations across a shock. In other words, the T2 over T1 and P2 over P1 equations as a convenience, and since we're used to doing that. But keep in mind that MAS is not equal to M2, even though M1 and MS are the same. Let's go back to these equations in our stationary shock reference frame and copy and paste them here, and now modify them by transforming to the moving shock or absolute frame of reference. Equation 1 for mass becomes ρ1 Vs equal ρ2 Vs minus Vas, where I've used the equations for V1 and V2 from our transformation. Likewise, the momentum equation becomes P1 plus ρ1 Vs squared equal P2 plus ρ2 Vs minus Vas squared. And equation 3, the energy equation, becomes H1 plus 1/2 Vs squared equal H2 plus 1/2 Vs minus Vas squared. I'll call these 1m, 2m, and 3m, since these are the equations across a moving shock. Now let's discuss how to calculate the flow properties across a moving shock. The key is to understand the difference between static properties and stagnation properties. A so-called static property is defined as the property an instrument that's measuring temperature or pressure, for example, would measure if the instrument were moving with the fluid. In other words, at the fluid's velocity. This is how we define a static property. By comparison, a stagnation property is defined by bringing the flow to rest. Thus, it is the property that a stationary instrument, when I say instrument, I mean a probe of some kind, would measure if the flow were brought to rest isentropically. The difference is that static properties are measured moving with the fluid, and stagnation properties are measured if the flow were brought to rest isentropically. And you can see by comparing these definitions that static properties are independent of frame of reference, since no matter what frame of reference you're in, you would move with the fluid, at least in your mind, to measure the static property. But stagnation properties are dependent on the frame of reference. This difference is critical for calculating fluid properties across a shock. From this we know that static properties, like P1, P2, etc., do not change with frame of reference, but stagnation properties, like P01, P02, etc., do change with frame of reference. So when analyzing flow across shocks for static properties, we use the same equations as previously, regardless of the frame of reference. For example, P2 over P1 for an ideal gas is a function of M1 and gamma. T2 over T1 is a different function of M1 and gamma, etc. We use these same equations, except use AS as our subscript instead of 2. So instead of P2, we write PAS, and TAS instead of T2 for moving shocks, and we use MS instead of M1 for moving shocks. So we call this MS here and here. But MS and M1 are the same anyway, so this one is not as critical. But for stagnation properties, do not use our previous equations for any properties that are stagnation properties. For example, we again compare the moving shock frame of reference to the stationary shock frame of reference. For the stationary shock, both V1 and V2 are not zero, and our energy equation was always H01 equal H02. But for this same shock in a moving shock frame of reference, VAS is not zero, but V1 is zero, since this shock is moving into still air. In that case, H01 before the shock is H1 plus V1 squared over 2 by definition, but V1 is zero, so H01 equal H1 in this moving shock frame of reference. That makes sense because this gas is still, so there's no difference between stagnation and static properties. But H0 after the shock is the static property H2 plus its speed VAS squared over 2. Comparing these, we know that H2 is greater than H1 across a shock, and VAS is greater than 0 in this moving shock reference frame. Thus, H0AS is greater than H01 for a moving shock. This may be hard to grasp since we're so used to stagnation enthalpy not changing across a shock, but you can clearly see that since H2 is greater than H1 and we add some positive value, this must be bigger than this. A corollary to this is that T0 after the shock is greater than T01 before the shock, again for a moving shock. Finally, what are the equations for stagnation properties in the moving shock frame of reference? Take stagnation pressure, for example. P0 after the shock, using ratios, is P0 after the shock over P after the shock times P after the shock. Well, this just comes from our isentropic relation in terms of MAS, the same isentropic equation we've been using for a long time. But this static property PAS is the same as P2 in our stationary shock frame of reference, since it's a static property that doesn't change with frame of reference. So we can use the P2 over P1 equation from previously to calculate PAS, namely PAS is our shock equation P2 over P1 times P1. I'm not going to write out that equation here, but we can just plug that equation along with P1 to get our final equation for P0 AS. We do a similar thing with stagnation temperature after the shock. It turns out that T0 AS is 1 plus gamma minus 1 over 2 MAS squared times T2 over T1 times T1. Finally, if we compare this P0 AS to P02 that we would calculate from our stationary shock equations, we would find that P0 AS is not the same as P0 2. In fact, P0 AS is greater than P0 2. Same thing with stagnation temperature. T0 AS turns out to be greater than T0 2. So the bottom line is that we need to be very careful when dealing with stagnation properties across a moving shock. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3.